All right, good afternoon, everyone. I hope you can hear me clearly back there. I'm Thomas Anthony. I am a scientist with UAB IT Research Computing. I'm also the director of the Big Data Research and Analytics Lab at UAB. Not a lot of people know about us at UAB. We are the University of Alabama, but at Birmingham, we are not the football school, we're not the party school. We are mainly the research school in the state of Alabama. So we are an R1 Doctoral Research University. We have over $500 million in research expenditures every year. We are ranked 15th nationally in among public universities for federal funding, and number 31 among all federally funded research in the country. So, and we're still a very young university. We've been there about 42, 43 years, so that's still relatively young. Our main funding comes from NIH, the NSF, and NASA. One cool thing is that all the refrigerators on the International Space Station are actually built by UAB. So every time a shuttle goes up, we send up some refrigerators, and some come back after refurbishment. Now, I belong to the team which is UAB IT Research Computing, and our mission is to support and help enhance the research portfolio with computing. What we make sure is none of our UAB grants are not competitive enough for a lack of computing. We make sure we get that to our researchers. We help our researchers accelerate their research so that the researcher can focus on the domain. Every time I talk to a new researcher, I tell him, you do not have to worry about the computing. Leave that to us. You focus on your actual science and we'll provide you the tools, the infrastructure. And since we are a big medical research university, medical research is our big driver. So when we talk to researchers, first thing we ask is how can we help? And the first thing we look at them is, can we actually accelerate that research? Can we accelerate the pace of that research? Mainly, most of them have a lot of data processing. So we say, hey, how can we help you accelerate the data processing pipeline? Can we throw newer technologies such as GPU computing at your particular problem? And then finally, can we help them with emerging technologies such as the AI, ML, the machine learning, deep learning stuff that makes them more competitive for some of those bigger grants? Now, this is a simple example of one of our neuroimaging workflows. So when someone goes to a neurologist with, they might have some neurological disorder, so the neurologist usually sends them out for a scan, their data, so they get a brain scan, and then it comes on to our HPC platform to do all the data analytics, and we can also combine it with structured and unstructured clinical data like race, demographics, your family history, and try to give a much better picture back to the physician. And this actually came out of one of our workflows that we did where we accelerated the Parkinson's research. And this was what we did. So when our researcher came to us, he was taking years to do that research, and usually that's not very good. By the time we came to the spring of this year, he could run his entire data set about 3 times a day. So you can imagine how that could help a researcher try out different models, try out building different stuff. And this was just a pure high-performance computing approach. Another approach we took was trying to include GPU computing as well. So this is an example that we had from the Human Connectome project. So it's about 900 folks were scanned. We have the genomic data as well. And this was again a brain imaging part of it. So one issue that we faced was one of our researchers was taking over our entire cluster, because every image that they were processing was taking them about 520 hours per subject. That's about 21 days per subject to do the research. So you can imagine, even if we gave them, say, a 900 cores on a cluster, it would still take them 21 days to do that research. So what we did was, initial work we did, we said, let's see if we can parallelize your work and get it running as fast as possible. We could help them with that. And then we asked, can we run that on the GPU? As you know, NVIDIA GPUs are very good at doing some of that work. And that's where we introduced the GPU. And that's when we realized that the user was using only the CPU version of that software. It had a GPU version of that software. So we worked with them, helped them refactor their code, and we brought that down from 21 days per subject to 2 hours per subject. That's a big improvement. So you can imagine how quickly our researchers can get their workflows and their pipelines done. And just as an academic exercise, we split it across 68 GPUs that we had. and we could run it in 40 seconds per subject. So that entire workflow that would have taken 21 days, even on a 1,000 core cluster, could be run in about 2.5 hours. So you can imagine the possibilities that come along with it. So you are not just limited to doing one thing. You can try out different combinations. Hey, I want to look at what if this tract in the brain goes from the hypothalamus, say, to the brainstem. How does that change? How does that change the outcome of my research itself? So they are no longer limited. The third application is we're not only helping them accelerate their application, but also look at some of the emerging technologies. Because we're doing medical research, we do not expect our physicians to be experts in AI, machine learning, deep learning. That is where we come in as well. We provide some of that expertise to them. We already have the NVIDIA GPUs. We can already accelerate the computing. Can we help build those out for them? So this came out of one of my projects where we were actually trying to figure out hemorrhages in the brain. And I only have 2 slices put up. And the right 2 slides are actually the inferencing. So the rightmost column is the actual hemorrhage. You can see it's fairly accurate as to where it has pulled out. And the center column is actually the edema around the hemorrhage. So as you know, whenever there's something which is abnormal in your brain, there is some swelling that goes along with it. And as you can see, you can't see the edema too well in the actual DICOM slices that I have put out on the left. But the the convolutional neural network that we applied to it was actually able to do this very quickly. And we could run through an entire brain of, say, 512 slices in about 30 seconds. And this is a machine that has actually picked out both the hemorrhage as well as the edema. So, say, suppose someone has a stroke, and not every hospital has a strokeologist to say, all right, this person has a stroke in the brain. And usually, so if the medication that you give, that's your clot buster, its efficacy decreases if you give it after 4 hours. So if you can get that to them, or at least get this scan in front of a radiologist's workflow quick enough that say, hey, look at this because we want to give that medication to the person, you can imagine how quickly, how much of a quality of life can be changed out of that. So what we have done is, how does it impact that real world? Our researchers are no longer constrained. We can improve the quality of care that we give. And as a medical research university and as one of the top 10 biggest hospitals in the country, that is big for us. How our researchers can try out new approaches. In the NIH world, it has always been a hypothesis-driven approach, but now we can show some of those data-driven approaches as well. And the NIH has started funding us. In fact, our last RO1 actually scored a perfect 10, and that was for schizophrenia. And we had some conversations with our program officers, so they would actually fund all of that, but it looks to be good. And these approaches can be used on multiple applications, some which are directly related, and some which actually came directly out of left field. Like, we've applied the same thing to accelerate our Parkinson's, Alzheimer's, pathology slices. Schizophrenia was the RO1 where we scored the first percentile, stroke, hemorrhage, cancer tumor screenings, and the others that I have put in, I cannot officially put it on the slide, but if I can detect a tumor inside a brain, I can detect weapons when you walk through an airport. Just something to think about, right? Inside the brain was actually way more complicated by doing surface scans, and so you stand at an airport and it is a TSA agent who looks at you. So you can imagine we even have developed that, and right now Homeland Security is testing that for us. So the applications just tend to be really broad in what we can do. And we could not do it without the help of our partners. Like DDN is one of our biggest partners in this. We have about 12 petabytes of storage right now, high-speed storage running on EDR InfiniBand. It's completely DDN. We have the 12K and the 14K, and as DDN always does that to me, the moment I buy a piece of hardware, they come out with a newer version of the hardware, and now they have the 18K out there. So we could not have done it without our partners. We have DDN as one of our big partners. Almost all our servers are from Dell. NVIDIA helps us a lot with the GPU stuff, and we have IBM's GPFS running on the DDN hardware. Bright is what manages our cluster itself. So, and one specific partner I would like to call out is the National Institute for Computational Sciences at the Oak Ridge National Laboratory, because they helped us accelerate some of our stuff on the CPUs and GPUs as well. So we only have so many scientists and software developers in our team. So it is a team sport, as you can see, and we work really well with our vendors. Any questions? And I think that's about it. I said I would talk fast so that you guys can get into the drawing quicker. So any questions?